So this is the subject fabric engineering. If you kindly allow me to show you a couple of slides about our institute. So I am from Indian Institute of Technology, IITs. In India we have about 23 IITs. So I am from IIT Delhi. So this is our institute, and we have about 8 engineering departments, some science and humanities, and we have some about 11 research centers. These are centers of excellence for specialized area, and also we have 3 schools. This is a very specialized institute only for engineering education. Okay. So we have a textile department where we run undergraduate, postgraduate and PhD program. There are many areas in which our department is doing research work. You can see some of the areas mentioned here. Okay, this is a brief introduction for me. Mostly I work in fabric manufacturing and textile structural composites. So the subject is fabric engineering. What exactly the fabric engineering is? Fabric engineering mainly depends on the selection or design of a suitable fiber, and using that fiber how to design a fabric. So this particular presentation based on how to manufacture a fiber, particularly the polyester, so that a fabric of desired hand value can be produced. So when we say engineering fiber, basically we talk about a structured fiber. So what exactly the structured fiber is? Look at this. This is engineered fabric. In the right hand side you can see the gentleman who is making a fabric. He knows what exactly he is making. He knows his application, and that's why he has made this intricate structure. So this is just a background. Based on this I will be covering these heads. What are various issues in fiber engineering and issues in fabric engineering, hand values, about polyester, because this fabric is mainly on polyester, and some analysis. If you look at the current clothing trend all over the world, people are going for basically the functional fabric. Means we want a special functionality in a fabric. So obviously we have to start thinking from fiber stage and fabric manufacturing stage. The most important is there is a fast changing fashion, so the time available to design a product is very, very short. So how to prepare or design or manufacture a fabric at a very short time? It needs clear-cut understanding of the engineering design aspect of the fabric. That means we are shifting from experience-oriented manufacturing to system of engineered manufacturing. For that we take the help of CAD system. Broadly in weaving, our CAD is broadly divided into 2 categories. One is CAD for artistic design another is CAD for engineering design. So we are talking about CAD for engineering design, where we decide the raw material parameters, weave parameters, and the weaving process itself. So when we try to design a fabric, we try to understand first the objective measurement of fabric properties, because unless you know what properties we are intending for, it is difficult to decide the construction parameters, and it is also difficult to predict the properties required in the final fabric. Then what is in fiber engineering? Textile engineers can do lot as far as fiber manufacturing is concerned. We talk about first softness or tactility, that is called what I call market value of the fiber. Then we talk about the processing capability of the fiber. I have given its name the mill value. Then what exactly we see the relationship between these mill value and the market value. They are very much dependent on the DPF, that is the denier per filament, that is fineness of the fiber. This fineness controls both the things. So what exactly the textile or fiber engineer do well? Fiber engineer can do many things. They can produce the fiber of any denier, any cross-sectional shape, any extensibility or mechanical properties, any length, any dimension, and of course even at the polymer stage one can develop many fibers like homopolymer taking cationic acid diagonal polymers, and also at the can give some additives to have certain properties. So in this research we have tried to make some fiber properties so that a desired fabric hand value can be made. So definition wise, what is structured fiber? Where we try to make a particular structure to get a desired hand value. Structured fiber is just a concept. We try to obtain a composite yarn, or we try to combine two or more fibers of different intrinsic characteristics. So basically, the problem is to understand what is the biomechanical functional performance relationship with the surface and morphological characteristics of the fiber. If you look at these morphological characteristics of the fiber, which decides the biomechanical functional performance of fabric, we broadly divide the fiber properties into three categories: macrostructure, microstructure, and submicroscopic or fine structure. Macrostructure means it basically deals with length, diameter, and crimp. Microstructure means basically the surface properties and cross-sectional shape, and submicroscopic structure means the dimension, shape, and composition of the polymers. So in this case, the research is based on only the deciding the cross-sectional shape. After the fabric is developed, the characteristics is linked with only fabric hand value. The reason being why hand value is taken as the point of reference, because we all know a fabric sells by heft and hand. Hand is basically a textual properties. When a fabric comes in contact with your skin, what is the perception of skin about the fabric properties? That is what called the hand value. When we produce the fabrics taking different fibers and measure its hand value, you can see there are 15 different fiber composition and fabric samples are produced, and their hand values are measured, and see what is their hand value. Here the result of hand value is shown both for winter and summer applications. So it's very clearly, you can see these are 15 different types of fiber. The result shows the polyester fibers mostly show very poor hand value compared to cotton, wool, and other fibers. Then we try to analyze what's the reason why the polyester is showing the poor hand value. Based on that, some decisions has been taken. So polyester gives poor hand value as compared to cotton, wool, and other natural fibers. That means this fact prompted textile and fiber scientists to explore various possibilities. So what possibilities could be? If you look at the properties of the polyester, definitely it's a dominant fiber all over the world. It's a highly versatile fiber. It has many plus points. Most of the plus points are mentioned here. However, the polyester, although it is dominant, it can be blended with many other fibers, but it has the main drawback is moisture absorbency, the low moisture transmission capability, lower hand and comfort values, and low weighting capability. So a thought process has been introduced how to enhance these parameters so that a high quality polyester based fabric can be produced. Okay, I can skip this one. So the question is how to enhance hand of a polyester. It needs some analysis. The analysis is like this. We try to understand the role of these parameters on the hand value of the polyester fabric, starting from filament configuration, filament extension, filament fineness, and the cross-sectional shape. If you look at the whole range of commercial fibers available in the market to make polyester fabric, these are available in two forms, either in spun yarn or filament yarn. So filament yarn is more prevalent. The filament yarn is characterized by these three, because these are the only four forms in which the fiber is available commercially for weaving. Either it is a flat or twisted or texture or intermingled. So you can see the structure of these four different fibers. So using these four configuration, there are several fabric samples are produced taking single or combination, and the hand value of these fabrics are measured, and the result shows that F1 and F2, which are giving the highest hand value for winter applications, and for summer applications you can see the 10 and 11, that is textured, flat textured combination gives the best hand value. So the inference of this exercise is the THV is very, very high when we take the combination of intermingled and intermingled for winter applications, while the presence of twisted warp and to some extent the flat yarn gives better THV for summer applications. Now, what is the role of filament extension? Similarly, different polyester fibers of different degree of extensibility has been produced. You can see here there are 5 different types of polyester fiber having extensibility starting from 6% to 30%, and the fabric samples were produced, the hand value are measured, and you can see here how the extensibility influence the hand value. There is a general feeling earlier, as you go for extensible fibers, the hand value increases. But as you can see from this result, it's not like that. The extension at a given point gives the best hand value. That means there is a need to optimize at what extensibility the fabric will give the best hand value. So to produce a soft touch ladies thin dress material, the samples were used for ladies dress material. Normally we think that higher extensibility is preferred. However, this study shows the optimum residual extensibility is about 24%. If you go beyond this, then again hand value falls. Then we try to understand what is the role of fineness, which is expressed here in terms of a DPF, that is denier per filament. So a wide range of denier per filament has been taken, starting from 0.6 to 4, and the last one is a mixed denier. That means 3 different denier is mixed, and the fabric samples are produced and their hand values are measured, and you can see the result. As the denier per filament increases, the surface characteristics MIU is the surface roughness goes on increasing, and MMD, that is the, which is basically the another surface properties, that is called the coefficient of friction, goes, not much change. And this is another interesting result, which is called the primary hand value. Primary hand value means a specific hand value with a specific mechanical properties. So what we conclude from this study is denier for filament has a direct bearing with total hand value. The effect of texturing with fiber fineness gives additional advantage. So texturing plays its role irrespective of the fineness of the fiber. And air permeability is suppressed using microdenier filaments. Then we finally tried the fibers with the different cross sections. In this study, the cross-sectional shape or the role of cross-sectional shape is determined in terms of the shape factor. So the role of fiber cross-section is expressed in terms of shape factor. I will show you how the shape factor is determined. Then what is the role of shape factor in determining the fabric hand value is determined. So look at what is the shape factor. Shape factor, which is expressed by the diameter equivalent from perimeter to the diameter equivalent from the area. Normally we express by 4 pi upon p square. That means if the cross-sectional shape is a circle, this shape factor is equal to 1. As you go on deviating from the circularity, then the shape factor value goes on decreasing. So taking this concept of shape factor, all the properties are determined. Also, the other parameters or other mechanical properties, that is called the bending rigidity of the fiber, is very highly influenced by the shape factor. And why we take the bending rigidity, as you know, if you look at the contribution of different mechanical properties on the fabric hand value, the bending plays an important role. The role of bending or the contribution of bending in the fabric hand is to the extent of 35% compared to all other mechanical properties. That's why the bending has been taken as one of the major parameters to understand what is the role of bending, and we indirectly relate the bending rigidity of the fiber of different cross sections. So bending rigidity, for which we calculate the bending stiffness of fiber of a different denier. You can see here the two different yarn produced using a fine fiber and a coarse fiber. The bending rigidity, from the concept, the bending rigidity of a cross section depends on the neutral axis. So what is this concept of neutral axis? I will show you different cross sections where you will find the neutral axis in different cross sections are different, and the rigidity depends on what is the neutral axis of the cross section. For example, when you try to produce the fiber of a different cross section, let's say circular, octagonal, square, dumbbell shape, trilobal, hexalobal, this is tibial, rectangular, and plus shape. So these are the different shapes. You can see the neutral axis in each cross sections. Then after determining the neutral axis, the bending rigidity is determined mathematically. So this is the rectangular cross section. The bending rigidity of this cross section is determined by the bending rigidity of circular cross section in terms of area divided by the bending of the triangular cross section, which we call ratio of bending rigidity. Because why we calculate ratio, we try to find out what is the change in rigidity compared to the circular cross section. So circular cross section keeping as a reference cross section, so what is the bending rigidity of other fibers cross section is determined, and mathematically we determine, taking all the cross section, what is the bending rigidity ratio. Then we calculate what is the relationship of this bending rigidity ratio with the hand value of the fabric in terms of rigidity. The reason being, the rigidity is a major contributor to the fabric hand. As I said, bending rigidity is responsible to the extent of 35% of the hand value. Even this relationship has a very good correlation with the experimental bending rigidity ratio. You can see here the theoretical bending rigidity ratio and the experimental bending rigidity ratio, they are more or less exactly same. So we try to calculate what is the relationship between bending rigidity ratio with the experimental bending rigidity ratio. We conclude from this the concept of bending rigidity about neutral axis of a different shape can be implemented in fiber cross-sectional shape for designing a fabric of different hand values. This is bending rigidity ratio of yarn with the fabric. We all know as the rigidity of a fiber increases or decreases, accordingly bending rigidity of fabric increases or decreases. So in this concept, we get exactly the same result. I can see both the curve follow almost the same trend. So the inference is the bending rigidity of a rectangular shape is lowest theoretically and experimentally. As the area distribution comes close to its neutral axis, bending rigidity reduces. So bending rigidity mainly depends on where the neutral axis is in the cross section. And accordingly, the rigidity of a different cross section changes. Then finally, we try to understand what is its relationship with the fabric hand value. So in fabric hand value, the cross-sectional shape are taken. These are 13 different cross-sectional shapes. So these are the cross-sectional shapes: circular, octagonal, square, dumbbell-shaped trilobal, hexagonal, TVL, rectangular, plus C-island, split, micro, and group multilobal cross-sections. So for all the cross-sections, we calculate what is the primary hand value and total hand value of the fabric. And what we got, the result is the THB, both for winter application and summer applications. And we found there is a strong relationship between the bending rigidity ratio of different cross-sections with the hand value. So from this study, what we finally conclude, change in cross-sectional shape of a filament influence the low stress mechanical properties, which is the main contributor to the fabric hand value. That is what the basic finding in this research. We have also a strong relationship of transmission behavior to know the thermal comfort of the fabric, which is also influenced by these cross-sectional shapes. Again, the same cross-sectional shapes are taken for this research, and we calculate what is the weakening behavior and thermal conductivity, the relationship of thermal conductivity with the shape factor, the diffusibility with the shape factor, the Qmax value with the shape factor, and also the thermal resistance with the shape factor. And we find a very good strong correlation, even MBTR, with the shape factor. So what exactly we conclude from this? There is enough possibility to design a fiber cross-sectional shape where you can control not only the mechanical properties and the hand value of the fabric, but also the transmission behavior of the fabric. That is the final study. We have an alternative approach to design a fabric by expert system, where we don't really go to the designing of a fiber cross-section or fiber geometry, but you can play with the weaving parameters to make a fabric of a desired hand value. So quickly I will show you. Normally, this is the traditional route of designing a fabric. We do it in every weaving mill. So this is, you can see here, how a designer really go about to make a fabric, which is a heat and trial method, and it is definitely time-taking and expensive method. But if you want to do it with a CAD system where one can control the design parameters by developing a suitable CAD, one can also find out, or one can also predict the properties of the fabric, particularly the hand value. So in this case, what we try to do is, we try to avoid this hit and trial method where we basically dependent on intuition, skill or experience of the designer, but we try to develop an expert system which is called engineering design of a fabric. What we try to do in expert system, we use some models. The model can be a geometrical model, can be a mechanical model, or can be artificial neural network model. In our case, we have tried this with an artificial neural network model. This is how this NN model works. We first develop a knowledge-based system from which we predict what will be the properties and performance of the fabric. To make this knowledge-based system, you need to develop different samples and to have enough database so that you can predict the properties and performance of the fabric. So in this case, we use this expert system from where we start from the designing process till the final fabric is produced and properties and the performance is finally predicted. In this case, we developed this system based on a specialized software where there is a dialog box. This is a user-friendly system in which we go on giving the input data. The input data starts from, let's say it is for a shooting fabric, so you have to first give what end use, because we are predicting the properties for hand value. So when we talk about hand value means a specific end use, whether it is winter application, summer application, shooting or shooting, ladies or gents. So that is first to be assigned what is the applications. Then we go for giving the input for the fiber percentage. As you can see here, the polyester percentage, so it's a blended fabric, so 55% polyester and other one is wool or cotton or any other viscous fiber, so that is fiber percentage. Then you give the input data for the fabric design, weave design, that is twill or plain or satin. Then you give input for the weaving parameter, that is peak density and end density. And similarly, there are different dialog boxes for giving the input for different parameters. And finally, the prediction takes place. So in the prediction, we find out different properties. And in this system, I'll show you the final result where the prediction value is very, very interesting, where the coefficient of correlation is something about 0.9384. So this is a specialized CAD system based on ANN prediction, where one can predict the hand value of a fabric from the fiber parameter, weave parameter, and the construction parameter of the fabric. So this is another way how a fabric can be designed by weaving technology and construction, deciding the construction parameters. Okay. Thus, the system provides a dynamic solution to fabric manufacturing with respect to design guidelines. It's a very quick response system because it's a user-friendly system. You can change the input data depending whether you want to change the weave or you want to change the fiber parameter, you want to change the weave parameter. So it's a very quick response system, and it can be used as a very good tool for the product development. So there are many possible opportunities for engineering fabric properties by fiber architecture. The first one was by changing the architecture of a fiber, one can change the hand value of a fabric. Then the shape factor can be taken as one of the key indicator in deciding the fabric properties. As you have seen, the shape factor has a very good or strong correlation not only with the hand value but with all transmission behavior of the fabric. A multi-directional understanding is required to optimize the cross-sectional shape to achieve the ideal polyester fabric for different properties. And finally, the CAD system. ANN-based embedded expert system is an efficient and reliable tool for fabric engineering because of built-in learning ability. The built-in learning ability is very, very important, And in a country like India or maybe in China, where thousands of fabric samples are available, you can enrich the database so that the system can be highly reliable. Basically, it's a knowledge-based system. If you give on feeding as many as the data as the in the knowledge-based system, the prediction becomes more and more accurate. So it's a very strong tool to predict the fabric properties if the database is very, very strong. Thank you.
Begin. Prediction of interface pressure development on compressible body for knitted tube. Please. We are late now by about 50 minutes.
Grabbed it and decided to visit. It's not coming. Okay. It's not coming. Okay, now. So you decided to come to this country. So the topic of this research is the prediction of interfacial pressure developed on compressible body by knitted tubes. Now there are many applications of use of knitted garments on human body where pressure is used as a therapy for mitigating many diseases like orthopedic disorders, venous and lymphatic disorders, for scar management, sports uniform, and body shaper stockings. Factors that affect pressure generation, mainly the characteristics of the human body and the tension that develops in the knitted tube or the sleeve. In the body characteristics which becomes important are the curvature of the body and the compressibility of the body. The tension that develops is a part of the garment fit, the way the garment is designed. Now here are some standard pressures by the different standard institutions of German, British, French and CN, and they have decided that light support will need such kind of pressures, medium, strong, heavy. We can see that there is a difference in opinion between these 4 different standard institutions in the world. But roughly we can say that light means the pressure will be between around 10 to 15 or so, medium is around 15 to 20, strong pressures develops when it is around 20 to 36, heavy pressures could be more than 36 or so. And now pressure, how much pressure gets generated is decided by this well-known Laplace law, which is very, very old law, and this law is still valid in many applications. And it is a very simple relationship where the pressure is a function of tension, T in the fabric of the knitted tube that we put on the body, and is a function of the radius of curvature, that is 1 upon r. There are many formulae that has been proposed by many researchers, but if we go through these formulae, though they look different, but the origin is the same, that is the Laplace law. Now this slide gives an idea about the way the principle of pressure generation. On the left hand side you have a body, and the human body, let us say, looks cylindrical, and there is just pressure stocking, and if the feet is more, that is ease of the garment f is greater than 0, that is the garment size is more than the body size, then obviously the body will never be compressed and no pressure will be generated. In the second case, the size of the body and the garment that fits on it are exactly same, and hence the body does not get compressed. So in this case also will not get any pressure. In the third case, which are known as pressure garments, where the body size is much more than the size of the garment. So when such a knitted tube, which we call pressure garments, is put on the body, the garment will get stretched, and therefore it will be able to generate transverse pressure on the human body. Now, we carried out certain experiments to start with a PVC cylinder, which is a rigid body, and this cylinder was then surrounded by a foam, which is representing the flesh, the human flesh. And then we put a knitted sleeve around this and measured pressure using a pressure sensor, which is Kikuhime pressure sensor. So this looks like this, that you have a bare PVC cylinder, a foam of 2 mm, and then on the bare PVC cylinder, we are putting foam, and we are measuring the pressure using this pressure sensor. The other one, there is one more PVC cylinder, where the bare cylinder itself is about 4.5 centimeter in radius. The previous one is a bare cylinder of 3.3 centimeter plus a foam of 2 mm. That makes a cylinder plus foam, and the total diameter is 4.5 centimeter. So as if this is a rigid cylinder of 4.5 centimeter, and the other one is a 4.5 centimeter cylinder, which is not really rigid. The inner part is rigid, and the outer shell is made of foam, which is compressible, like a human bone and the flesh around it. The foam characteristics is shown by this graph, that is pressure versus thickness relationship. And when the pressure was measured using that sensor, the graphs that we see here, what we see that the reduction factor definition is given on the top. It is the cylinder circumference minus the knitted tube circumference divided by cylinder circumference multiplied by 100. This proportional decrease in the size of the knitted tube that we are going to put on the cylinder. And this particular graph, if you look at it, the rigid cylinder, the foam covered cylinder, and the other one graph that shows the pressure estimated on the basis of Laplace law. What we see that the pressure measured on the rigid cylinder and the pressure estimated by Laplace law, they are tallying quite well. Whereas the other one, where this rigid cylinder was covered by a foam which is compressible, we see that there is a tremendous departure from the one where only rigid cylinder was used. It basically means that the Laplace law is not estimating pressure correctly when the surface of the cylinder is compressible and not really rigid. In the case of rigid cylinder, there is a perfect match. Now this differences that why we are not in a position to estimate the pressure based on Laplace law. We decided that probably we have to go for a different approach for estimating the pressure. And the approach that we took is basically an approach where we are equating the energy released by the fabric tube while it is trying to compress the cylinder that is covered with foam with the compressive energy required to deform the foam. So what we feel is that the moment we put the knitted tube or knitted sleeve on the compressible surface, it is going to compress it. So some energy that is being released by the fabric is being used to compress or deform the foam, which is compressible. So if we can calculate these two energy and then equate them, we'll be able to predict the pressure that it develops. So based on this idea, we moved ahead, and typically the fabrics, the knitted fabrics or tubes were basically made from some cotton yarn as well as some spandex fibers, and the typical curves are shown there, and that sort of curve can easily characterized by quadratic equations. Again, this connection is lost. It is not very stable here. How is it? Signal. Okay. So the equations, the fabric load elongation graph can be characterized by these quadratic equations, and the energy released because of the fabric, which initially is traced to a value E epsilon 0 to epsilon 1. We can integrate this equation to find it out. So this is what was done. And we could similarly find out, we could characterize the compressible behavior of the foam by another quadratic equations. And we could find out the energy that is released by integrating this equation. And so if I know these are the two equations which are characterizing the energy that is released by the fabric, the left hand side, and the right hand side describes an equation which describing the energy released because of the compression of the foam that you get. And you have to equate these two. Before that, we need to know the constants which are there. There is A, B, C, the equation which is on the left hand side, and also the two more constants which are there on the right hand side, alpha and beta. So these equations can be determined from actual experimentation of the fabric and the foam that is there. So if we have this two, then like this is the equation that we got for the pressure deformation. For the foam that you used, the constants are shown in the equations. Similarly, the other one is this. This is for the fabric, and the equation is shown there with the R-squared value 0.9644. So these are two empirical equations which are fitted, and we could find out the energy terms from here, and based on that we have found out what is the value of the pressure P that develops, and these are the energy that is released that we have calculated for different reduction factors or different size of the tube. And the last table shows that the pressure that we can predict based on Laplace equations, based on energy considerations for different reduction factors. And if you look at these data, you will find that at the reduction factor 10, let us say the energy consideration is giving 9.7, the actual value that we have measured is giving 9, whereas the Laplace equation gives 13.5. If you see all this data, you will find that the energy consideration is giving me a better prediction, especially when I am actually trying to measure the pressure on a compressible body. So the conclusions are that the pressure generation at the interface of a fabric tube and a foam covered cylinder was always less than the recorded on a similar rigid cylinder when the diameters of the two cylinders are same. Laplace law was found to estimate the pressure exerted on a rigid cylinder more accurately than that on a soft cylinder surface. So if it happens to be a rigid cylinder, the Laplace equation is good enough for prediction. Prediction based on energy consideration was found to be more accurate for soft compressible surface, so it will be true also for human body. And energy principle could be used for predicting pressure on human bodies from a given knitted slip. So this is what was done, and we are going to publish a paper which will be coming very soon in Journal of Industrial Textiles. Thank you.
Any question?
Yes, please.
Yeah, please.
Regarding to the foam material,
Foam.
which the foam, yes, you have used the foam
Yeah,
material
right.
instead of the human skin. I mean, a big difference between the foam and especially the moderate specificity of the foam and the human. So we would like to make low pressure in the human body just in order to close, no closing for the blood vessels. So I think I did mention the moderate specificity of the two things, the difference between the foam and the human body. So did you predict that, especially on the human body?
Yeah.
Otherwise, we will find the side effect of the pressure on the human body itself.
Yeah. On the human body, we are actually taking some trials now. We have generated some data, but we have not yet able to publish it. I'm not able to show right now. But we are taking trials on human body also, especially on the arm. We're trying to measure it. But the difficulty is the compressibility of the flesh, which is here.
Yeah.
How to know this? And this data is not generally available. By foam, I can measure it. At different pressure, I can find out the thickness which is changing. But here, if I want to measure it, I have to have some instrumentation or some data somewhat available which can give me some idea about the compressibility of the tissues which are here. And that also varies from human to human. Every human being is not same. So you need to know the range about which it varies. It also varies between male and female. And according to age also it varies. So a lot of factors which are there to characterize the compressibility of the tissues which are there in the arm as a function of male, female, age, toddlers, children,
Yes, but this
adult.
is mainly on the foam. So I don't really how to compromise between the foam and the human body.
No,
So this is
the
one.
next step. is to go for different order. The first step is to just check whether the energy equation is going to predict correctly or not. So once we have established this, the next step is to go for definitely humans as well. That is the finding. Thank you. Thank you very much.
Any question?
Thank you.
It's a pleasure to have present to you, and I would like to thank the committee for inviting me here. This project is again collaboration between NEC State University and also Alexandria University. Ahmed Hassanein was a student of mine a few years ago, and he was working under my direction, and Dr. Rafat Mashali and Ibrahim Lawari direction. Okay. Most of high-performance fibers are vulnerable to UV. They get weak after subjecting them to UV. We use them to protect lives, such as bulletproof vests. They are used also in giant scientific balloon for NASA and other high-performance products. So it is really unfortunate to have this fiber with such impressive use hindered by UV. To have UV stabilizer, in organic or inorganic, you cannot load these during the spinning, because if you load them during the spinning, you will weaken the chains. You are going to interrupt the chain continuity, and the fibers will become weak. So there is no way to do that. Their ability, like Kevlar and Xylon and other fibers for high performance, you cannot dye them to protect them from, some dyes protect from UV, so it is difficult to dye them. One approach is to use a protective layer loaded with UV and cover the fiber with such layer. So our objective was to do a computational model to predict that the coverage or protection of the layer, to protect what is under the layer. In fact, what we did after that, we had a braided structure that used a stand-in for huge scientific balloon for NASA. NASA has scientific balloon that would accommodate inside it 2 football fields, huge size of balloon that goes about 10 kilometers high altitude and carry payload with equipment that discover planetary and discover issues in the ozone layer and such. So our objective is to have such model, and we're using particle size of nanoscale. And we would like to verify the model experimentally. And the target is to design protective layer for high performance fibers without having too much trials and errors. So we have assumptions. The particle shape is sphere. All particles have the same size, and you can buy actually particles with certain limit, so you don't have really variation, much variation, very small variation. So these assumptions, the 2 assumptions, are really very close to real situation. And the particles are randomly distributed in the protective layer film or film. The thickness of the protective layer is uniform. This is our assumption. So the idea here is to have computational region or computational volume, which has 3 dimensions, and then in that volume we are randomly throwing these spheres. And once one sphere took a place, occupy a place, that place is occupied. You cannot have another sphere sharing the same sphere that was there before. So we had a very complex tracking of and monitoring of these particles that we put in that computational space. We studied here the volume of, we have here the N, which is number of UV protective particles, spheres. A is the length of the film in a computational region, and B and C width and thickness. Volume fraction of VV particle is V sub F, and V sub B volume of particle, which is sphere. And D is a particle diameter. So we can calculate this relationship, and we can come up with VB as you see it right there. Okay. We created a program, and the computer program creates a position for each sphere. And the sphere has 3 points, right? A point, that's the center of the sphere, has X, Y, Z, and we have I as tracking I from 1 to N. N is a number of particles, and we can calculate that based on our choice of the fiber volume fraction. And here are the conditions that we put there. And then we have random, stand for random function generator. We generated all these points. And then the computer program checks whether any particle overlaps with a previously positioned particle. Once we have overlap, we reject that position, that new. And L is the distance between center of 2 spheres. So if we have 5 spheres there, the computer will go check number 6 against the number 5 that previously done. And if it shares the volume with any, it rejects it and then try another one. Okay. The projection area here, we have fibers in space, 3D shape, thickness, you have thickness and width and length. But we look at if the ray comes to the film, we think it's going to face all the particles. So we thought if we can take all the particles and project them in XY plane. So after we're done with the program, we do what we call projection on a plane. XY plane, so that all the area, all the volume becomes an area rather than volume. So this is what we do here. For every sphere, we're going to project it on any XY plane. Doesn't have to be the origin, the one that is with the origin. So we create that projected area, and then we take images from MATLAB, and we look at this area. We can also measure the area covered and the area uncovered by looking at black and white areas that we can measure that by a computer program also. We created the numerical results, and we're going to start looking at these results. This is the effective view particle diameter. If we change the diameter, here is 3D visualization on the left, and this is a projection on the right. And if you look at this here, we have the particle of diameter of 25 nanometer, and we have 3% volume fraction. Then we increase now, same thing, but we play with the diameter. The diameter was reduced from here to here, 25 to 20, and then to 15, 10, 5, and you can start seeing the effect of reduction of the diameter, so the nano becomes even more smaller, and then you can see the area covered by that. And here is, we are looking at if we have fiber volume, I mean the volume fraction of the spheres, 3% and 6%, you can see how much you can cover using more just 60% increased by 3%. So we have here two parameters showing the particle diameter and the effect of volume fraction of the nanoparticle. You can see here all side by side from 25 to 5 nano. You can see the area covered. Effect of volume fraction. We played with the volume fraction, which means more particles. We add more particles, and then if you have 10%, we change it from 2% to 10%. You can see here, and this is a summary of the results. We are looking at the area covered, the projected area covered, and the volume fraction for two diameter, 15 and 20 nano. So you can see what happened in the area increased, and then effect of protective layer thickness, and we were able here to increase the thickness in micron. If we increase the thickness and keep only 2% of fiber volume fraction, you can see we could reach to almost 100% with such small amount of nanoparticles in terms of volume. We're looking at the thickness again and fiber volume fraction from 2 to 4, and the diameter is 50 nanometer, and we were able to do the entire curve till we reach about 100%. Okay. We looked at the model and said, what happened if I do random? Is it really random? Random supposed to give you 0 deviation or almost 0 deviation. So what we did here, we repeated the trials for this run, and we did it for other runs. So we repeated this over and over and over to look at the percentage of area covered with the number of trials, and we found it's almost constant. So our model is repeatable. You know, the randomness is really randomness, is true, because we were suspecting that we are removing some of the particles because it shares a volume. So what if we check that and make sure that model is reliable, which we found out it is reliable. Before I conclude, we did a real work to take that model. This model actually is ideal model. The problem with nanoparticles, they agglomerate. They try to tend to get together, and separating them is difficult. What we're showing here is ideal, and we're showing this as benchmark. If you really want to reach to that level, you have to separate the nanoparticles effectively. You must find a way to do that by ultrasonic, by agitation, by some chemical treatments. It is important to do that. When we try to do this practically, adding these, and we use several methods like twin screws while we are extruding. We extruded a film around the braid. And this technology is available, and we said let's do that and see if we can really show practically if we can do that. And we took SEM images, different layers, and we found out it is very difficult to separate the nanoparticles. They agglomerate, and we had to increase the thickness to achieve protection. Further work was done when we took this at different level, as you saw that, different parameters, and we looked at the UV vis to look at the protection level, and you were able to see as you increase this parameter, as the model predicted, the direction is okay. However, the amount you need to achieve this protection is higher than what the model says. Again, the model is a benchmark, is ideal that we need to achieve to reduce the thickness. NASA wants to have protection. However, that layer must be thin, and the increase in weight is important to them, because instead of having by the way, there are 80 kilometers of braid that support the balloon. So 80 kilometers is a lot of weight. If you add 10% of that, you can imagine how much weight you add. So we would like to have a thin, very thin film. And to have an effective thin film, you have to look at how to separate these nanoparticles. We're working on that still with NASA. The NASA supported us for maybe 6 years' work. We've done a lot of work. This is not the only work we've done for NASA, but this was part of it. And we were able to verify the model. We used cylindrical. Also, cylindrical was found to be giving you more coverage than sphere. And we were able to verify the model, at least the trend. We verified that and we published paper later. Okay. I finished that, and I would like to acknowledge the government of Egypt funded that, because Ahmed Hassanin came on a fund from the Channel program. We did this before actually NASA supported the next stage. We had NASA supported stage before the Ahmed came, and then after Ahmed came also we had more work with NASA and more financial support. And I acknowledge NASA for that as well. Thank you very much.
Bismillah ar-Rahman ar-Rahim. Impact of spring ultraviolet radiation on color value and bursting strength of the knitted fabrics. Teamwork, Dr. Muhammad Sultan and Dr. Abu Bakr Mito, and I am Dr. Iman al-Tahan. Daylight from the sun, which contain ultraviolet radiation, reach us through the Earth's atmosphere. Textile materials provide a simple and convenient protection against UV radiation. Alteration in the fabric construction parameters with suitable finishing methods can be employed as UV protection fabrics. UV rays can break down the chemical bond and thus fade the fabric colors. In work, studying the effect of xenon light and weather conditions on color value and bursting strengths of the knitted fabrics. Material and methods. 24 knitted fabric samples were investigated, which were suitable for outerwear in spring and summer. The sample include different knitted structure like single jersey, rib and interlock, and double knitted structure. Sample include different materials from cotton, viscose, and with and without lycra yarn. The sample were investigated without stretch and dry conditions. The properties that were measured for the fabric samples were wales and coarse count, loop length, stitch density, fabric weight, fabric thickness, and fabric porosity. For each fabric type, there are two samples. The first was subjected to xenon light, and the second was exposure to spring weather in the time range of March 2019 till in June 2019. The samples which subjected to xenon light were entered to ultrascan spectrophotometer to measure its color value before and after subjected. The samples which exposure to weather were divided into 4 parts according to the exposure time. The first part with exposure 500 hours, and the second 1,000 hours. The third one 1,500 hours, and the last one 1,800 hours. Each sample was divided into 2 parts. The first directly tested, and the second washed, then dried, and then tested. The tests which were carried out on the samples before and after exposure to UV radiation were color value and bursting strengths. Our result and discussion divided into 2 parts. The first part studied the effect of exposure to the knitted fabric to xenon light on the color value, and the second part studied the effect of exposure time on knitted fabrics to weather conditions in the period of spring from end March to end June on the color value and bursting strengths. The fabrics were divided into several groups according to its finish. First group contain gray fabrics, different design. As we say, this group contain 5 samples. Its specification showed in table 1, and the table 2 show their xenon test result. As we say, the percentage of reduction in color value according to xenon test is slightly lower because the gray fabric is contain wax and the pigments which act as a sunscreen. The figures, the first 2 figures show the effect of exposure time on color value before and after washing, and the second 2 figures effect of exposure time on bursting strength. As we see, in the 2 figures, as the exposure time increase, the color value decrease before and after washing, and the bursting strength by exposure the time also decrease. Second group contain gray fabric, cotton with and without lycra. This group divided into contains 3 fabric samples. Its specification showed in table 3, and the table 4 contain the xenon test result. As we see, the sample 1 has higher percentage of reduction because it hasn't any lycra yarn, and also the first two figures. The first 2 figures show the effect of exposure time on color value before and after washing, and the second 2 figures effect of exposure time on the bursting strength of the fabric. We can see the the fabric sample 3 has higher color value and bursting strength because the presence of lycra yarn on it. Group 3 bleached cotton fabric, different designs. This group contains 4 fabric samples. Its specification showed in table 5, and table 6 contain the xenon test result. The fabric as the same manner in the previous figures, with increasing the exposure time, the color value and bursting strength decrease, but in color value we can notice that after washing the color value decrease than before washing because of the chemical detergent in washing process, but in bursting strength we can see we can notice that the bursting strength after washing increase because of the fabric shrinkage. Group 4 light colors dyed fabric. This group contains 6 fabric samples. Table 7 show its specification, and table 8 color xenon test results. As the same manner previous, the exposure time with increasing the exposure time, the color value and bursting strength after and before washing decrease. Group 5 dark colors. This group contains 4 samples, and its specification showed in table 9, and table 10 contains the xenon test result. We can also see notice that the percentage reduction in color slightly lower than the light colors. As the same manner, the exposure increasing the exposure time, the color value and bursting strength decrease. From the result and discussion, it can be deduced that number 1, resistance against the action of xenon and sunlight is higher in gray fabric compared to bleached fabric due to the existence of pigments and waxes. The color change in white fabric under the action of xenon and sunlight has better resistance than dyed one, which often leads to widespread discoloration. Knitted fabric construction and properties play a great role in resistance of dyed colored fabric due to exposure to xenon and sunlight. The reduction in color value due to exposure to xenon or sunlight depends on the type of dye, the structure of dye molecules, the present absorptive group, and depth of dye, taking into consideration the different fiber type. The value and rate of bursting strength loss with increasing the exposure time for the same fabric design varies in according to the state of the fabric, gray, bleached, or dyed either light color or dark color. Clothing manufacturers could use the information from this study for better design of sun protective clothing. Thank you.
Thank you for that. Any question?
Yes, please. The fabrics are exposed for 2,000 hours. If we say 8 hours a day,
2,000 hours.
yes. If you say 8 hours a day, means 212 days, means 1 year, our third year. So why we didn't use the ultraviolet can affect or can fix the strength and time. So you don't need really to expose the fabrics to the sun. So why?
The period of our study from end March to from March to end June. This
Yes, I'm asking. Why didn't use the ultraviolet? You can fix it, the time and the strength of the ultraviolet in the lab, not in the weather, under the open weather. So you can save time. You can, just because you expose the fabrics 200 days. Well, why you didn't put it in the lab and then fix it the ultraviolet, the strength?
And the microbial and every umbrella in the library we have not umbrella. In Egypt we have dust and we have a weather which is finishing. I'm not working with her, but it's better to use the actual condition than to use the laboratory condition.
There are different parameters now, not only the ultraviolet. So.
No, it's when I will when you go, there are two systems when you go to sun to have a what it is in the beach. You can go to ultraviolet and you can go to the beach. There are difference. There is big difference working in actual condition and working in laboratory. It's from my opinion, it's better to have actual condition. No, it's easier. It's easier to have apparatus for working but it's not the real estate. It's not the real estate.
I think more better than the laboratory. Yes. Because the natural conditions is different from weather. And weather in Egypt, or not weather in India, and not weather. More accurate, give more accurate results. I think that
I can make an experiment. Ultraviolet, take this cloth, and it's not working in every country like this. If you go to in Suez, they have no ultraviolet like Egypt. If I put the ultraviolet, this condition it's not real. This is results in Egypt weather, so that it is not in all over the world.
Well, now under the weather, not saying ultraviolet or dry or wet or humidity or how much or all these parameters you have to consider.
Yes, I agree. It has to be saying it's actual condition. No, it's okay. Okay, thank you. I have no, it's not for me. There are some I have to give. He said, it's not my work to give. They give me paper, I have to give it to all. Okay. Thank you. We have the last paper is not coming.